So last time we got to one of the central ideas of this class, which is if you have a surface in 3 dimensions, at every point there's something called the tangent plane, right? So we have a point P, and this surface we call M. We call this the tangent plane at the point P of M. And what is the tangent plane? Does anybody remember the definition of the tangent plane?
It's the set of all velocity vectors.
Yeah, all velocity vectors at the point P of a path in the surface M, right? Just think of an ant walking on the surface M. What are all the possible velocity vectors that ant can have when they're at the point P? And that's the tangent plane. And then we had this really cool thing, which was called the shape operator. And I would say this is the first sort of concept from the class that is, goes beyond multivariable calculus, right? I mean, what's the difference? Because you're doing 3-dimensional geometry a little bit in multivariable calculus. This definitely seems like it's not multivariable calculus anymore. It's going beyond. And so the shape operator at the point P, it's a mapping from the tangent plane at the point M to the tangent to itself. So you have one shape operator, for each point, right? And what's the definition? Well, when you put in a tangent vector v, could be any tangent vector v, you do the following. Well, first of all, we have this. Just remember, we have this unit normal vector field, capital U, that's perpendicular to the surface everywhere. Has length 1, is perpendicular to the surface, and it's pointing out everywhere. It also could be pointing in everywhere, right? We have a choice. As long as it's perpendicular to the surface everywhere. And what's the relevance of this U? Well, in particular, it tells you something about the tangent plane, right? Because the unit normal vector U here is going to be exactly perpendicular, right, at length 1, and it'll be perpendicular to the tangent plane, right? So if you really want to understand a plane, right, just give me a point on the plane and give me its normal vector, and that tells me the plane, right? And so as U changes, that tells us how the tangent plane is changing. And that's going to tell us something about curvature. And so we define the, so given any vector v here, which by the way does not have to be unit length, but it could be. We define it that the rate of change of u in the direction v is the definition of the shape operator. Okay. For u, again, is that unit normal vector. Now, why is there a minus sign there? Does anybody remember why there's a minus sign there? Just convention, historical. Has no meaning, significance whatsoever. Okay.
Could you explain the mapping thing again? How?
So the point. So here's what your question is going to is. I've explained that v has to be an element of the tangent plane, right? By definition, because I want to know u is only defined on the surface, right? So I can only take the derivative of u in the direction along the surface. So this wouldn't even make sense if v wasn't a tangent vector, right? But what's not so obvious is why is the result here? Why is the result here in the tangent plane as well, right? And that's this argument that we're going to be using 17 times in this class, which is that since u dot u equals 1 everywhere. Why is that? Because by construction, u has length 1 everywhere. If we then take the derivative of this, okay, so take the derivative, the directional derivative in the direction of v. Okay, take the directional derivative of both sides. Okay, so by the way, this is our notation for directional derivative, right? You put a function in there, and that v takes the directional derivative. We write it this way in this class. Then if you take the directional derivative in both sides, you get, well, the derivative of 1 is 0. And then you take the directional derivative of u dot u. And then by the product rule, this is equal to twice u dot product the covariant derivative in the direction v of u. Now, that means that this vector and this vector are perpendicular because the dot product is 0, right? If the dot product of two vectors is 0, means they're perpendicular. And so therefore, this derivative of the unit vector u, its rate of change in the direction of v. And that's the covariant derivative. It's like a directional derivative, but for vector fields. We write it differently. When you're taking the derivative of a function, you write v of f. You put some function there, right? When you're taking the directional, so that's the directional derivative of a function. The directional derivative of a vector field you write this way. And the point is we know that since its dot product with u is 0, these two vectors must be perpendicular. But if you're perpendicular to u, that's the definition, essentially, of being in the tangent plane. Okay. I mean, you could say u is defined to be perpendicular to every path, right? Velocity of any path and so on. And so this gives us the shape operator. Any questions about what I've done so far? I'll tell you what's kind of cool about this is like you've all had linear algebra, I think, or maybe you're possibly now taking it. But what's interesting about this linear, but even if you've had linear algebra, what's interesting about it is it's kind of an abstractly defined map, isn't it? Right? Like there are no basis vectors. Like normally when you map R2 to R2, right? Or R3 to R3 or something like that, you would still have an ij and a k, right? Or an i and a j, like there's x-axis and the y-axis, right? Here we're just mapping a plane to a plane, but guess what? It's still a linear mapping. Okay, and so you can still think of it as, it's kind of like taking this, it's like sort of like the xy plane to the xy plane, which, what are linear, by the way, this is a linear mapping, I didn't actually prove that yet. Why is it linear? Well, it's because of multivariable calculus. If you take the covariant derivative, let's say in the v plus w direction of u, this equals this. And also, if you take the derivative, if you multiply your v by a function, in this case we can just multiply, it's a mapping each point, so I can just multiply by 5. How about that? By the way, the v and the w are vectors too, so for right now I'm going to put these vectors in there. Sometimes I won't. This equals 5 times. Okay. So when we say linear, I mean these two properties. Right? So it's linear in this slide. It's linear. This thing here is linear in v. Right? What it means is that if I replace v with v1 plus v2, I have the first identity, or v plus w, I have the first identity. And if I replace v by 5v, that 5 just factors out. All right, and that's these are multivariable calculus facts. And so what we have, therefore, but this v is that v, so we have a linear mapping from this plane to itself. Okay. Now, what are examples of linear mappings? Okay, so let's do an example. You could do, say you have the xy plane here, right? And you want to map it to itself. Okay, so I'll put it on an arrow where it's mapping to itself. What I could do is I could say, x bar, y bar is equal to, let's say, 3, 2, 4, 3 times xy. This is an example of a linear mapping. Okay. So in particular, it'll give me any point xy, it'll give me another point x bar, y bar, and it does it in a linear way. It's matrix multiplication, right? So for example, 0, 0 gets, the origin always gets mapped to itself. That's one of the definitions of a linear mapping, because if I replace 5 with 0, right, then, because by the way, there's nothing special about 5 here. Any number would factor out, right? So it means that when I put in 0, I need to get 0 out, right? And so linear mappings are, they always fix the origin by this definition. And now what happens to the point 1 comma 0? Say this is 1, that's 0, you do your matrix multiplication, you get the point 3 comma 4, right? So 1, 2, 3 comma 4. So then what you would say is like this vector here gets mapped to that vector there, right? Oh, this would be 3 comma 4. So everybody understand what linear mapping is? And so what are some of the basic features of linear mappings? Well, they have eigenvectors and eigenvalues and determinants and traces and things like this, right? And so, but we have a linear mapping here, which is clearly geometric, right? It's telling us about the rate of change of u, right? So it's telling us how our surface is curving. So we figure this shape operator thing is geometric, and therefore its eigenvectors and eigenvalues must have, and its determinant and its trace must be geometry. It must be telling us something about how the surface is curving in the three-dimensional space. And we can do an example here. Let me just go ahead and follow the example in the book. And so I'm going to, for my reason, let me change the matrix here. This was a pretty good matrix, by the way, because the determinant's 1. You guys see that? 3, 3. Do y'all remember how to compute determinants? A times, it's this times this minus that times that, right? So the determinant's 1, which, by the way, means that the inverse matrix will have integer values. Do y'all remember how to compute the inverse of a matrix? 2 by 2 matrix?
Yeah, sure.
Okay. I'll write down here off camera. But by the way, I think we are being recorded. I don't think I mentioned that before. But something you're supposed to know anyway is that the inverse matrix of this 2 by 2 matrix is let's see here. You switch the A and the D, and then you put minus signs on the C and the B. Is that right? And then the AD, yeah, and then you divide by the determinant AD minus BC, right? Did I do that, guys, right?
Yeah.
So that's the inverse of a 2 by 2 matrix. I did not have the inverse of a 3 by 3 matrix memorized. But there are, but it exists as long as the determinant's not 0, right? And there are algorithms for computing it. And if you're like, why is that the inverse of a 2 by 2 matrix? Well, just multiply that matrix with the original matrix and you get the identity matrix. So it just works. Okay, but let me change this matrix here to match the example given in the book. So what I got here? 4 minus 2, 3 minus 1 is the example they have in the book here. And then, okay, what are some of the basic things you learn to do in your linear algebra class? One is to compute eigenvectors and eigenvalues. Right? So, for example, we want to find a vector such that when you multiply it by this matrix, the vector just gets scaled, right? It gets multiplied by a constant. So, in other words, we want to solve the problem 4, 3, minus 2, minus 1 times, let's say, AB is equal to lambda times AB. And when you can solve this problem, that's the vector AB is called an eigenvector, and this lambda here is called an eigenvalue. And so I'll refer you all to your linear algebra textbooks for all the details, but let's go ahead and work this example. I'll remind you how this works. The way you find eigenvectors and eigenvalues is this lambda here is also can be thought as just lambda times the identity matrix. So remember the identity matrix is just this, right? Why is that the identity matrix? Because when you multiply any vector by the identity matrix, you get the same vector back, right? It doesn't do anything. So if I put a lambda here, now this is multiplying by lambda. So multiplying by lambda is the same thing as multiplying by this 2 by 2 matrix. So equivalently, we're trying to find an A and a B such that this times A, this matrix times AB equals that matrix times AB. If I subtract both sides, then what I get is, I'm going to subtract this from both sides, and I get a 4 minus lambda here. I get a minus 1 minus lambda there, and then a minus 2 here, and a 3 here. Equals 0, 0, if you like, right? It's a 0 vector. Any questions so far what I did there? Just subtracted this from both sides. And then you're like, wait a second. How is it possible for a matrix to take a vector and send it to 0, right? Especially if it's a non-zero vector. We're looking for A and B that are non-zero, right? So how can it send a non-zero vector, a matrix and a non-zero vector to 0? Well, the only way is if the determinant of this matrix is equal to 0. Now, you may remember, like, why is that? Okay, well, remember what determinant was? We actually reviewed this a couple of weeks ago. But remember that the determinant is actually, if you take a 2 by 2 matrix and think of the first row and the second row, right? And then and you graph them as vectors, right? The area of the parallelogram that they define is actually what the determinant is defined to be. And the only way to have a vector get sent to 0 is if that parallelogram has area 0. If that area, if anything other than 0, then it doesn't send any vectors to 0. But if it's a degenerate parallelogram, then it does. Okay, so the only way for this to be solvable is the determinant 0. So then the next step is you come up here and you say 0 equals the determinant of that matrix, which is 4 minus lambda times minus 1 minus lambda, and then this times this minus that times that, plus 2 times 3, which is 6, right? And so you get lambda squared. But guys, better check me here, okay? So minus. Wait a second. Did I do that right now? That's minus 3, because that's plus 1 minus 4 minus 3, and then there's going to be minus 4 plus 6 is plus 2. And so we can factor this as lambda minus 2 times lambda minus 1, right? And since that equals 0, then we know, of course, then that lambda is equal to 1 or 2, right? And those are your two possible eigenvalues. And so these are the tricks that you learn in your linear algebra class. And so then we say, okay, well, there's an eigenvector when lambda equals 1. There's going to be an eigenvector, AB equals something. And then when the eigenvalue equals 2, there's going to be a solution. Okay. And when lambda equals 1, then you can see what I have is 4a minus 2b. Or actually, let's go down here. It's easier to do it right here, right? If lambda equals 1, then I've got a 3 minus 2, right? And then, so it means 3a minus 2b has to equal 0. So I guess this is going to be 2, 3. Is that right? Does that work? Any multiple. By the way, it's not just 2, 3. Any multiple of 2, 3 will work. Is that right?
Yeah.
Okay. And if and by the way, it works down here as well, right? Because when lambda equals 1, we have a 3 minus 2 here as well, right? So it's the same equation twice. This is, not 2 equations and 2 unknowns solving for AB here. This is the same equation twice. Now when lambda equals 2, we get, and this example is in the book, we get have a 2 here and a minus 2 there, so we could just have this be 1 and 1. And when lambda equals 2, we get a 3 minus 3 here. So basically if A equals B, so any multiple of 1, 1, right, will be an eigen vector for that eigenvalue that lambda equals 2. Any questions? So that's how you find eigenvectors and eigenvalues. And then you're probably going to figure, okay, that's just an example. Okay, what does it mean? Well, guess what? The fact that, see, this thing here is very explicit, right? And here, what I want to distinguish here is there's a linear mapping here. And it's defined by this right here. And what I could do is say, look, there's a linear mapping R2 into R2, okay? And what I want to point out for you guys is there's a difference between this linear mapping and that matrix. One is a mapping and one is a matrix. The matrix is simply a way of representing that linear mapping. Okay? And then you can say, well, what does that matrix mean? Well, what it says is, in fact, let's just really think of it a little bit more abstractly. Okay? That in this example, if we have basis vectors 1, 0, and 0, 1, right? So then L is represented by a matrix capital A equal to 4 minus 2, 3 minus 1. Okay? But what if we don't have an x-axis and a y-axis? Because y'all see with the shape operator, there is no canonical x-axis and y-axis for our planes, right? So what if we say, no, you can't, you're not allowed to, think of the x and y-axis as special, right? In which case, we shouldn't even be representing this linear mapping that way necessarily, right? What if instead we use different basis vectors? Let's use the basis vectors. How about we use the eigenvectors and eigenvalues? I mean, that's a nice one, right? How about we use 2, 3 for the first one? And then the second one will be 1, 1, okay? Well, then L is represented by this, by this matrix A equal to, well, if these are my basis vectors, what does this mean? What it says is, we'll say that L sends let's see here. I got letters here. A. I don't want to use A and B. Okay, so we'll say C 1, 2, 3 plus C 2, 1, 1 to K 1, 2, 3 plus K 2, 1, 1, okay? Where K1, K2 is equal to that matrix A. By the way, since we have an A there, I'll call this A tilde. A tilde times C1, C2. Okay? So in other words, if I take my input as a linear combination of these two vectors, right? And I think of my output as a linear combination of the two vectors, then there's some sort of linear relationship between the C's and the K's, right? And let's suppose, and in other words, since it's linear, it must be by some matrix multiplication. Now, what is that matrix multiplication? Well, it's just the eigenvalues here. It's 1 and 2, right? Along the diagonal. You guys see that? Because what do I know? I know that 2, 3 is an eigenvector, right? When I take L and I apply it to 2, 3, this K1 would get multiplied by 1. And then the C, so in other words, K1 is equal to C1, and then K2 is equal to 2, C2. So I need this A tilde to equal that. So actually, what we have to, the way I want y'all to think of these linear mappings now is, let's get away from a canonical x-axis, y-axis way of thinking about it. And let's just say, no, choose some basis vectors, and then let's think of everything in that tangent plane as a linear combination of those basis vectors, right? And let's see how these coefficients change under the linear mapping, right? That's what we want to know. And then that gives us a 2 by 2 matrix, which is going to, for the same linear mapping, I get two different matrices if I have two different bases, right? So my choice of basis vectors will affect how I represent it, okay? And you can see, like, for this example, it's kind of silly. Well, why would you ever choose anything other than the standard set of basis vectors? Just seems like we're making things more complicated, right? But for our main application, we don't have a standard set of basis vectors. And so we really need to kind of think about what's the best. I mean, so what are I don't want to compute something that isn't really, that depends on something arbitrary, right? I want to compute geometric invariance, things that don't depend on my choices of basis vectors or how I represent something, right? Now here's the thing: so the question really is, what doesn't change? You see how A changed? A and A tilde are not the same, right? But there are some things about them that are the same. You want to tell me two things? There's actually two things about these matrices which have not changed, actually.
Trace and determinant.
Trace and determinant. The trace and the determinant didn't change. What's the trace? Trace means the sum of the diagonals. 4 plus or minus 1 is 3. 1 plus 2 is 3. Oh, what a coincidence. The trace didn't change. Not a coincidence. Trace is invariant. And then the determinant didn't change. What's the determinant? This times this minus that times that. So we get minus 4 minus a negative 6, which is plus 2. What's the determinant of this? This times this minus that times that. 2. Trace and determinant didn't change. So, okay, cool. So what we can see here then in both cases, right, is that the trace of A is equal to 3, and the determinant of A, this equals 2. Okay, so for our shape operator here, trace and determinant actually won't change. And I mentioned that last time, that the determinant of the shape operator at each point, that's what we call K, Gauss curvature. And the trace of the shape operator, in this class, we call it twice the mean curvature. And in every other geometry textbook and class you'll ever encounter in the real world, they just call it the mean curvature. So it's kind of funny how things work. Every book, now why do we call it twice the mean curvature? These are weird historical things, okay? But what are the eigenvalues? Let's look at this example here. And by the way, what do these eigenvalues represent? They represent, over here, the eigenvalues of the shape operator are called principal curvatures. So, we got eigenvalues and eigenvectors. The eigenvalues are called the principal curvatures. Principal, like this? Did I do it right, or is it AL? Maybe someone can tell me. Did I do it right?
Yeah.
Okay. And then eigenvector are the principal curvature directions. Is that what they call it in the book? Right, principal
direction.
Principal directions. Okay. And remember, eigenvector is only defined up to scaling, right? It's like really a direction, right? And so let me tell you, just as an example, what these eigenvectors and eigenvalues represent, and then we'll go back to some more linear algebra. If I have a cylinder, this is just for your intuition, so you get a little idea here, and you can check the fact this is true later. But just pick any point. I'll pick this point right here, okay? Y'all can see the tangent plane is mostly vertical, right? Guys, get the idea there, right? I mean, there's two, in that tangent plane, I mean, you have to guess what are the principal directions, right? I mean, there's a natural guess, isn't there, right? I mean, if I said, look, there's two directions that are special, one's along the circle there, and one is along the spine, right? And so, yeah, guess what? The eigenvectors of this are, in fact, those two directions. And guess what? They're always perpendicular, which is interesting. And geometrically, one of them is the direction of maximum curvature, and the other one is the direction of minimum curvature. You see how it's curving? The biggest curvature is in that circle direction, right? And then the least amount of curvature is along the spine, right? And so when you maximize and minimize sort of cross-sectional curvature, actually, because given here's your U, right? Here's how I kind of like to think of it. I actually like to call it cross-sectional curvature. The book calls it normal curvature. But if you'll see normal curvature discussed, you'll be tested on it. Whenever they use the word normal curvature, think cross-sectional curvature. Because I have a capital U here. Now let me take a little u here. You guys mind? The book does this all the time too. They use u way too much, okay? So I'm just following the book. So otherwise it gets too confusing. Little u is a tangent vector. Capital U is a perpendicular vector. That's their convention, okay? But do you see that two vectors define a plane, right? And the cross section is going to be that circle. Do y'all see that? If I take the surface in question is the cylinder. But if I take the plane defined by capital U and little u in this example, I get that circle, right? Now, little u is any tangent vector, so I have a whole circle of possible cross sections I can do here, right? If I say take the cross section where the curvature of the cross section, which is a curve, right? I mean, when you take a cross section, this surface, which is two-dimensional in 3 space, is a curve in the two-dimensional cross section, right? And if I say maximize that the curvature of the cross section at that point, then you get that circle, and that's your one of your eigenvector directions, and one of your principal directions. And whatever the curvature of that curve is, that's the principal curvature, or the eigenvalue. And then you can also minimize. When you minimize the curvature, you go to the other direction. It's always perpendicular to the maximum. And that's the curvature of that cross section is actually, which is 0 in this case, because it's a straight line. That's your other eigenvalue, and that's your other eigendirection, your other eigenvector. So we'll prove that here pretty soon. Maybe today. I'm not sure. We'll see. Definitely this week. Okay, so in other words, there's cool geometry going to come out of this, but we really need to go back to the linear algebra to understand it. Okay, like how do we actually prove these things? Question, yes.
And when you said that those represent minimum and maximum curvatures,
Uh-huh.
was that like intrinsic, like part of the definition, or is that just like a special case?
No, it's always the case.
Okay.
It will prove it. It will prove it in this class here pretty soon, this week, if not today.
Okay.
Yeah. Okay, so now let's realize we got some linear algebra to do. Okay, so let me just review some more linear algebra. I say review. I'm not positive y'all have seen it quite in this context. Okay, where there's not like a canonical twice the basis vectors, right? But the first thing I want to do is let's convince ourselves that actually trace and determinant are in fact invariant. I mean, it's nice that it works in this example, right? But what's the fundamental reason for it? It's because this A tilde is equal to, what's the relationship between A and A tilde? Okay, there's some relationship, and we can use matrix multiplication to do it. Yes?
It's just conjugation like this.
Yeah. So we're going to, there's going to be some other vector B, and this is going to be the relationship. Now, what does B do? B takes coefficients like C1, C2, and K1 and K2 and converts them from one basis to the other basis, right? And so let's say it converts it from the A tilde basis to the A basis, right? Okay, so if I had coefficients that were appropriate for A tilde, then I hit them with B, and so you multiply on the right here with your and then multiply it. You hit it with B. Now these are coefficients that are appropriate for A. Hit A with it. The output is appropriate for A, so now I have to hit with B inverse to get coefficients back that are appropriate for A tilde. Okay, so it's an exercise to show that this is the case. And so I'll let you contemplate that. But then you have to know two facts. So here are two facts you need to know from your linear algebra class. I won't prove them. The determinant of m times n is the determinant of m times the determinant of n. And the other fact is that the trace of m times n is equal to the trace of n times m. Okay? Those are both straightforward things to verify. The trace thing is just look at the formula. Do y'all remember what trace is? Sum of the diagonal elements. Just work out what this formula is. Work out what that is. They're equal. Okay. I wouldn't suggest doing that for this proof. I suppose you could do that. But that seems like a nightmare to me. The way I would think of it is, let's say, I'll just do it for 2x2 matrices, right? So we have an xy plane here, and we hit it by m. And we get to a mapping here, and then we hit it with n, and we get a mapping here. Okay, so multiplication by a 2x2 matrix is a linear mapping, right? So I could do hit by m then n, and I could do it the other way around. But what is the determinant? Well, it's how much. If you have some, remember if you have a square, then it gets mapped to a parallelogram, right? Like this. Agreed? And this square is a unit square, so it's area 1. And whatever the area of this is the determinant of M. Okay? So what the determinant of M is how much this unit square, its area gets stretched by, or I guess sent to a parallelogram, and however much its area gets stretched by is the determinant of M. But guess what? That's not just true for parallelograms, because everything is made up of little squares, right? So more generally, if I have some region over here, right, I can think of as a bunch of little squares, right? And then it's going to get stretched, right, to some region over here, and each of these things is a bunch of parallelograms. Okay, my artwork's not perfect, but you guys get the idea, right? These squares get stretched to parallelograms. But the point is that each of these parallelograms has the determinant of M of area, whereas each, times the area of each of those little squares. So actually, the determinant of M is the stretching factor of volume. And every region over here, area, sorry. The area gets stretched by the factor of determinant of M. So it's how much areas get stretched when you do a mapping. So it doesn't really matter the order, right? If I stretch the area by 2 and then 3, or if I did it the other way around, stretch it by 3 then 2, right? I'm still doing a total stretching of 6. Does that make sense? And so what's the total stretching? That's the mapping like this, by the way. That's M times N, right? I should write it the other way because we're operating on the right. Sorry. First you multiply by M, and then you multiply by N. So the point is that the total stretching, in other words, the determinant of N times N, that's the 6, right? That equals 2 times 3. Okay. So that's the proof of the first identity. And the second one is just calculation. Okay. Do y'all appreciate this review? Okay. Slash stuff they maybe never said out loud, or I don't know. I have no idea. I've never taught linear algebra, by the way. You want to hear another funny little secret? I never took linear algebra. It's just not the way they did math back in my day. I guess I took a lot of calculus and so forth, and then I guess at some point you were just supposed to know it. And okay, and I just picked it up. So in other words, all this stuff is figure outable. All right, so enjoy your. Actually, linear algebra is a pretty cool class. Any questions before I start erasing here? Okay, so because of these identities, and we have this relationship here. Well, now what you can see is that the determinant of A tilde is equal to, using this first rule, it's going to be the determinant of B inverse times the determinant of A. When you use the rule twice, right? You get this. But the determinant of B inverse and the determinant of B, they multiply to 1, right? If I really wanted to play around with things, this is the determinant of A times the determinant of B inverse B, which is the identity, right? The determinant of the identity is 1, so this equals the determinant of A. So now we see the determinant of A and the determinant of A tilde are going to be the same. Cool? And then as far as the trace thing goes, well, the trace of A tilde is equal to the trace of B inverse times A, B, right? So let me put the times right there. And now the trace of two things, I can switch the order of the two things, it doesn't matter. So this equals the trace of the second, I got the first thing and the second thing, right? So I get A, B times B inverse. See the trick there, guys? And then B times B inverse is the identity. So this equals the trace of A. Pretty cool? Okay. Okay, so, all right, so that justifies defining the determinant of the shape operator and the trace of the shape operator as things that doesn't matter. You might say, well, what is the matrix representing this linear mapping? Like when you compute a determinant, ultimately I need a 2x2 matrix, right? And so you're saying, well, what set of basis vectors are you going to use to define your matrix? And the answer, it doesn't matter. Anything you want, suit yourself. Do you guys get that? any 2 by 2 representation will give me the same trace and the same determinant. So it doesn't matter. Pick any, I can choose any stupid 2 vectors I want as long as they're linearly independent, right? Represent the linear mapping with respect to those vectors, and the determinant and the trace won't matter. Yes?
They don't even have to be in the plane.
They have to be in the plane.
Yeah,
Any
okay.
2 vectors
I
in
was
the
gonna
plane.
say,
Yeah,
yeah.
exactly. Yeah. Other questions, comments? Okay, cool. It gets better. You guys promise to remember this? Well, you got, I mean, look, okay. Here's, let me just, is this, I think of y'all as pretty early in your mathematical careers. Okay? Calculus is a starting point, not end point. Isn't it funny how some people used to think calculus was the end of math? Like, why would you ever need to know calculus? Okay, that's a starting point. Everything before that is warm up. Okay? It really is the center of math. How about that? Can we call calculus the center of mathematics?
Seems
I
like
think it-
linear algebra is now.
Well, linear algebra is pretty important too. I agree, but calculus with limits, integration, differentiation, stuff like that, right? You know, like the shape operator, yeah, it's linear algebra, but we had to. There's your calculus right there, right? Yeah. So this is just the beginning. But here's a rule I hope you live your life by. It's like life advice here, okay? And that is, don't ever use a theorem you can't prove yourself. Don't think it's funny how I call that life advice. But it's really true. It's really math advice, right? In your math classes. Try to understand, like, it really should make you uncomfortable if you're quoting a theorem that you don't know how to prove, right? Like, if you're saying, well, determinant trace of m times n equals trace of, I use that fact, right? If you don't know how to prove that, or you haven't proved it before, you should write that down on a piece of paper, and then later, when you have time, either prove it yourself or look it up. Okay? It's actually super easy. Just do it. Just work it out, actually. And then do that with every single thing. And then what you're going to find out is that everyone has gaps because everyone had different teachers, right? And then just start filling in all the gaps. And this will make everything easier, actually, in the long run. Because mathematics is not about memorization, it's about understanding. And try to become a person who can't ever forget a reason something's true. Like, it's pretty hard to forget something if you actually understand it, isn't it? Like, that's what you want to be. It's like, understand the reason behind this, right? It's not because I said so, or my math teacher in high school said so, or whatever, right? That's ridiculous, right? It's one of the great things about mathematics, right? Is that you don't have to take someone's word for it. So don't take people's word for anything. Yes?
Do you think that there's a difference between like demonstration and intuition though? Like sometimes I feel like I can go through the steps to show that something is true, but I don't intuitively feel like I get it.
Great question. I love it. We're not robots. There is something called intuition. And I think what you're getting at is examples. Like, see how we started with an example?
Mm-hmm.
And then we did the example, and look, the 1 plus 2 equals 4 minus 1. The trace is the same in both cases, right?
Mm-hmm.
That really should come first before we start proving things, that the trace is invariant, right? Don't you guys agree that should come first? Do 2 or 3 examples, and then it's like, wait a second, is this always true? Even if someone, look, I knew that this was already true, but I want to show you all that at least one example first, right? Because otherwise you're like, what the hell is he talking about? Wouldn't it be way harder to understand if I just gave the proof and we didn't do an example first? It'd be way harder. What is he talking about? Right? Guess what? I still do that. As a professional mathematician, I try not to do it. We start doing it secretly a little bit. Okay? So I'm just telling you the secrets, right? Well, I'm not allowed to put examples in my research papers that I publish, by the way. There's page limits. And they're like, if it goes out, you got this many pages, that's it, otherwise we're rejecting your paper, right? And so then you're not allowed to put in examples and this and that. And so if you read my research papers, could be a little bit intimidating. In fact, it's true if you read anyone's research papers. Anyone's research papers are kind of intimidating. You're like, whoa, no examples, right? Why don't they put some examples in here? And I think it's actually a little bit of a problem because now page limits, it doesn't even make sense, right? Like, everything's digital, right? So I understood back when they had to print the actual journal article and there was an expense and a cost and color cost extra and all this other stuff, right? But it doesn't make any sense today, right? So everyone's doing examples. They're just not doing it publicly, right? They're kind of doing it privately. So just always do lots of examples. What your homework is for. You want to, but yeah, intuition, have a picture in your head. One of the reasons to take this class, by the way, if you want to learn general relativity, is that this is the last class where there's actual genuine pictures. I mean, what I say is, the pictures get more abstract. How about that? Like right here, we have a picture. That's an actual surface in 3 dimensions, right? I didn't draw it, but there's a coordinate axes here, right? X and Y, Z, right? X, Y, and Z. And this is a surface in 3-dimensional space, right? But that picture isn't even a lie. It's like really there, right? And then when you get into the more, and so you're developing an intuition in this class, right? And then eventually this surface of this potato will become a space-time, like a 3 plus 1 dimensional space-time. But I can't visualize a curved 3 plus 1 dimensional space-time. And that's what I do. I don't think anyone really can, but I can visualize that, right? And so when I think curvature, I think of a surface of a potato in 3 dimensions. And you got to be careful with your intuition, though, because when you get a lie in your intuition, if your intuition is like you have examples that are wrong in your head, that can be devastating, can't it? Right? That's like we're in some ways where I'm limited, right? Is the way in which a surface of potato is not like a space-time. Right? There are some things that are different, and then that's the hard part, right? Like, oh, I don't even have a picture for that. Let me tell you some more stuff about the shape operator. It's a symmetric operator. And this, by the way, simplifies things significantly. So theorem 2.3.5, the shape operator is symmetric. By the way, what does that mean, okay? That doesn't mean, remember the shape operator, remember there's this linear operator L, it's different than its representation by this two matrix. So I'm not saying that the representation will be symmetric. And by the way, the representation matrix might not be symmetric depending on your choice of basis vectors, okay? But what does it mean? It means that V dot product the shape operator applied to W is equal to W dot product the shape operator applied to V for all V and W in the tangent plane at the point P. And that's what it means. So remember what's going on here. The shape operator takes a tangent vector. You apply the shape operator to it, you get a shape operator out, right? You get a tangent vector out. So that's a tangent vector, dot product of tangent vector, which is a number, is equal to a tangent vector, dot product of tangent vector, which is a number. And that's true for any two tangent vectors, V and W. Okay? Now how do you prove it? It turns out it's like 3 lines. Like that's one thing I like about this class. Is a lot of the most important theorems are just super short. And so I say it's super short. This one's actually kind of in the medium category. There's a step 1 and a step 2. Okay. So first, we have some identities. Observe these identities. Okay. First one is that the shape operator of xu dot xu equals something. Now, what was xu? Do y'all remember that you could choose any coordinate chart you wanted to? This is U, that's V. And then we map this in here, and we have a coordinate chart in the potato, some rectangle here. around the point P, right? This is x of u comma v, mapping into the three-dimensional space. Okay. So I'll write down here x of u comma v. And what are u and v? U and v is like latitude and longitude, right? Like if we want to have coordinates on the unit sphere on the Earth, we use latitude and longitude, right? And we did that example. But just let u and v be any two coordinates you want, and then so you get, an x of u comma v, y of u comma v, comma z of u comma v. All right, so that's our coordinate chart. And you might say, well, what coordinate chart are you going to choose? Which one? Because there's many, right? Doesn't matter. Turns out this doesn't matter. Just pick one. I don't care. That's one thing that's interesting about this subject is quite often you'll pick a coordinate chart, and then if you're like, well, which one? Doesn't matter. So don't have paralysis by analysis where you're like, well, yeah, but which coordinate chart should I choose, right? There's so many choices, and then a lot of people just stop there, right? You ever notice that in your own life? Like, you get stuck because, wait a second, there's like 17 choices and I don't know which one to choose. So you just don't make any of them. Paralysis by analysis. Here, just pick one. I don't care. And what does it equal? It turns out there's an identity. And this is equal to xuu dot product u. Okay? And the shaper operator of xu dot xv, this is xuv dot u. By the way, this proof I'm about to show you, I think I put it on the midterm like half the time. So you definitely would want to learn it. It's a cool theorem. It's a cool theorem. What's the definition of the shape operator? I would know that. Okay, that's like a give me problem, right? But prove the shape operator is symmetric. It's a great test question. Because it's beautiful. It really is beautiful. And yet non-trivial and not that long, actually. That's the thing about test questions. If they take too long to do, that's not a good test question, right? So the first, we have these identities here. Okay, so now I'm just going to prove the second one here. It turns out if u equals v, you get the other two anyway, right? I mean, I'll prove it for the middle identity there. And so it's actually quite cool. You say, so 0 is equal to, would you guys agree that the derivative of 0 is 0? So think about the function defined to be 0 everywhere, and then take the directional derivative of that in the direction of xu. Now you remember what xu is. This is a tangent vector, right? So at every given point here, right, I've got two vectors here. Any point in the tangent plane here. Well, should I draw? I'll draw another picture here, right? Use your coordinate chart. Any given point, you've got this xu and xv. And these are like the directions of the lines of latitude and longitude. Xu and xv. These are vectors. And they are, what is xu? It's the partial derivative of x with respect to u, which is the direction that x is going when you hold v fixed and increase u, right? So that's a partial derivative. This xv is a partial derivative. You guys have been doing homework on this, so hopefully that's good review. Easy? Okay. But what's another way to get 0? Well, it's u dot xv. Why? Because u is defined to be perpendicular to the tangent plane. Xu and xv are in the tangent plane. Fair enough? Yes?
Could you explain the middle part, like the directional derivative? Yeah, that part. The
Yeah.
x.
Okay, there's something to think about. Let me tell you what your brain should be doing. U is a three-dimensional vector, right? xv is a three-dimensional vector. This one's perpendicular to the surface. This one's tangent to the surface, right? But the dot product is a three-dimensional dot product, which means you get a number at each point. Another name for a number at each point is called a function, right? A number at each point on the surface of your potato is called a function, right? And then we can take that function and take its directional derivative in the direction of a vector. What's that vector we'll use? We're going to use xu. Okay? So this is something very clever here already, okay? This is a very clever setup, right? I mean, we went from 0, boom, something pretty complicated. Do you guys agree? Clever. Okay, so probably it would be easier if I said, look, this dot that is 0, and I'll take the XU derivative of both sides. But anyway, this is what we have, okay? And then we're going to use the product rule. I mean, we all love the product rule, right? We got the dot product there, right? Derivative, directional derivative should be a product rule, right? Now, when you take remember you take the derivative of the u, that's called a covariant derivative. So we draw it this way. So that's taking the derivative of the first thing. Remember the product rule, it's the derivative of the first thing times the second thing, in this case dot product. And then plus the first thing, dot product, the derivative of the second thing. Okay? But now you stare at this for a second, and you say, well, wait a second. This first thing here, isn't that the definition of the shape operator? Practically, except for a minus sign, right? And you're like, yeah, it's the derivative of u in some direction. So yeah, except for the minus sign. So this is the negative of the shape operator, right, of xu. And then we're dot producting it with xv. Y'all agree on that first step? Just the definition of the shape operator. And now that I want you to remind y'all of something. This term here, and I proved it, and I've done this trick already once, but now I'm going to do it again. When you take the covariant derivative in the direction of the vector field xu, that's just saying take the partial derivative with respect to u. Okay, and so this is just the partial derivative with respect to u of xv. So this is x vu. Okay. So I'm using the fact that if you have xu, and then you apply it to a function, right? That's how we write directional derivatives. It's different from your multivariable calculus class. That's a directional derivative. Function f in the direction xu. This is equal to d f, partial f partial u, which we're going to write f sub u. Okay. And so when I do this, remember what covariant derivative does. Covariant derivative says takes the derivative of each component of your vector field. But xv was just the v partial derivative of x, right? And so now we take in addition to a v partial derivative, we take a u partial derivative as well. So we get xvu. And what we've proved now is this identity right here, the second one, right? Because look, it was 0 equals this, so this is equal to that. This without the minus sign equals that. That's the second identity. Yes?
So x vu, is that the partial derivative of?
Yeah. So x v u is equal to the partial derivative, second partial derivative of x with respect to v and u.
Okay.
Which is a vector quantity.
Right, because x is a vector quantity, and so you take two partial derivatives, and you still have a vector quantity.
Gotcha.
Yes?
To the order of UV and VU, man.
It doesn't matter, right? It's something you learned from your multivariable calculus class, is that the order of partial derivatives doesn't matter, right? Y'all remember that? So the point is, and this is the key point. The key point is that we can see this thing as symmetric. Whether I had x, I could have xv here and xu there, I get the same answer over here. I mean, actually, I wrote this as xvu, but this says xuv, right? But it doesn't matter because xvu equals xuv. Partial derivatives don't matter. The order doesn't matter. And that's, by the way, is at the heart of why the shape operator is symmetric, because the partial derivatives don't matter, right? So in other words, I can switch xu and xv. In other words, what I've done is I've proven this symmetric property for xu and xv. Right? If I let this be xu and that be xv, then I can prove the identity, right, or vice versa. And then here's the last step of the proof. The last step, this is like step 1, is to prove these identities. And then step 2 is, well, wait a second. So let's call this star, right? So star is symmetric for basis vectors xu and xv. Done. That's all you need. The point is, we all know that, right? If you can prove something for basis vectors, then it's true for all vectors, right? Now, it's not exact. I skipped about a bunch of annoying algebra there. I'm going to erase this now, I guess. And this is where there's certain points in the class where I'm like, oh, gosh, I don't want to do this. Please. If I could just pay y'all like,
$80,000.
if I could just pay $20 and I have to do this next thing here, I would do it. Okay, it's definitely, but, okay, fine. You guys don't want the money, you want to see, right? So, it's just, this is the thing that you would often would not see, okay? Why is it true? Why is step 2 true? Well, the key point is, if I look at, A xu plus B xv, this right here, that spans the tangent plane, right? You guys get the point? I mean, the tangent plane is two-dimensional. You give me any two vectors, any linear combination of those two vectors will get me any vector I want, right? Okay. So in other words, what I can do is I can say, if I want to prove this identity up there, you say, well, let V equal AXU plus BXV. And let's let W equal CXU plus DXV. I mean, technically what you do is you say these two vectors span. Okay, so. Okay. And then if I want to prove my identity, star, I just say V dot product the shape operator of W equals AXU plus BXV dot product, and then I have to do the shape operator applied to W. Okay? But the shape operator is linear, but let me just go ahead and put it in first. See, I want to skip steps so badly, okay? You guys don't even understand how painful this is to do, okay? Okay, but I will do it. But I am suffering here, okay? And later on you will too, but we've got to do it at least once, right? Okay. It's not like I enjoy this, okay? AXU plus BXV. What does linearity mean? It means that this is equal to C times the shape operator of XU plus D times the shape operator of XV. Now, that's an important point. This is why we like linear operators, because we can do stuff like this. You guys get the point? Now you're like, why can you do that? Well, remember the shape operator is kind of like matrix multiplication, and matrix multiplication has a distributive law, right? Yeah, it has all the same rules as matrix multiplication. It's linear. That's what linearity means. Okay, and then you multiply this out. You see you're going to get 4 terms, right? And we get AC times XU dot product shape operator of XU. Plus AD times XU dot product shape operator of XV. Okay. Plus BC XV dot product shape operator of XU, I think. And then plus the last term is BD. Did I make any mistakes so far? And it's XV dot product shape operator of XV. You guys agree?
Yeah, you're good.
Okay. Which equals, now, here's the key point. All I need, really, the only thing I actually need is this identity right here, is that the shape operator of XU dot XV is equal to the shape operator of XV dot XU, okay? So this is really, like those formulas are to prove this, okay? And it's symmetric on basis vectors. So in other words, this term here equals that term there, okay? So in other words, this equals CXU plus DXV dot product, the shape operator of AXU plus BXV. Right, because I'm going to get an AC XU term, right? And I'm going to get a BD XV term. And then I'm going to get the same cross terms. And the point is these cross terms are all the same anyway. I'm going to get an AD term and a BC term. And because it's symmetric on my basis vectors, then it equals this. But then this is equal to, that right there is W. And this is the shape dot product, the shape operator of V. Okay, so we proved our identity. I mean, honestly, the way you'd probably work it out is compute this, and you get this mess. Compute this, you also get that mess. Oh, okay, they're equal. Okay? I probably did, I mean, be perfectly honest, I wouldn't work backwards like that, okay? I'd probably compute this, get the mess, get this, get a mess. You see, oh, it's the same mess. Therefore, they're equal. So in other words, but why do we suspect this would be the case? Like the pattern you learn is, if you can prove something for basis vectors, oh, it's a symmetric operator for basis vectors. By the way, if it's XU and XU, of course, it's the same expression, right? So obviously it's symmetric, right? So since it's symmetric for these linearly independent basis vectors, then it's symmetric for all vectors. And that's the proof. Now, why is this important? Turns out it's critically important. What this means then, remember do you guys mind if I erase this? Yeah? Any questions about this ugliness? Okay. By the way, you got to do that, right? We're going to work it out. We're doing all the terms. Convince yourself, right? And then throw the piece of paper away. Or you don't save it, usually, right? Okay. Why do we care? You guys remember what's nice about orthonormal vectors? Like if V is equal to 3I plus 4j. But what I love about it is that the way you get the 3 is that it's just equal to V dot product I. Right? Remember I is 1, 0, and j is 0, 1. Okay, we're not talking about, it's not complex numbers here, right? We're just using basis vectors I, j, and k. And then the 4 is equal to V dot j, right? And that's not just true for I and j, it's true for any two orthonormal vectors. If I have any orthonormal basis, I use dot product to find the coefficient. So the point is, because of this fact, let's choose an orthonormal basis for the tangent plane. Okay, so in other words, we're trying to figure out, well, what basis should we choose for this tangent plane here? I have an idea. Let's choose two vectors that are perpendicular to each other and have length 1. Okay, does that seem fair, guys? 1, 1. And we use these vectors for our basis, right? If you do that, then the point is you're going to get some matrix out, A. And this A that you get out, we'll call these E1 and E2, okay? Okay, so this will be E1 and this will be E2. And you'll say, well, which orthonormal basis? I don't care. Just pick one. Then what A will equal, by the way, when you do the calculation is, this will be E1 dot product shape operator applied to E1. This will be, now why is that? It's because when I plug in E1, if I take E1, you plug it in, and I get the shape operator of E1 out, right? But now if I want to know how many E1s are in that, well, I got to multiply product with E1, right? If I want to know how many E2s are in that, I got to dot product it with E2. You guys see what happened there? Okay, so I take E1, I plug it in, I get shape operator of E1. Okay, how many E1s is that coming out? I want to get everything with respect to E1. Dot product with E1 because it's an orthonormal basis, and only because it's an orthonormal basis, right? Then I get this formula here, right? And the same thing here for E2. When you plug in E2, I get the shape operator of E2 out. Okay, well, how many E1s are in that? Well, you dot product it with E1 to get the number of E1s, right, using this stuff. And then dot product with E2 to get the number of E2s. Okay, But the point is these two terms here are equal, right? Why? Because you have E1, E2, E1, E2. It's a symmetric matrix, right? So for example, this is going to be symmetric, such as, so I can say it's going to be of the form A, B, C, C. So be a symmetric, in other words, with an orthonormal basis, I get an actual symmetric A, okay? By the way, you don't get a symmetric A if it's not an orthonormal basis. Okay, so I have to use this orthonormal trick here, okay? Now, let's compute compute the, let's compute eigenvalues. So remember what you do, you say 0 equal to the determinant of A minus lambda, B minus lambda, C, C, which equals A minus lambda, B minus lambda minus AC. And then you'll see that if I were to graph this as a parabola, that's the lambda axis here, right? Without the minus A, let's see here. Minus, not AC, minus C squared, right? Minus C squared. So this has two roots at A and B, but then when you subtract something positive, it makes it go down even more. You're still going to have two real roots. Do you guys get that? And so what it means is we're going to get two real eigenvalues. They could be the same eigenvalue, right? It could be duplicate. But that's a theorem, okay? Two real eigenvalues. Lambda 1, and we call them lambda 1 and lambda 2. Okay, so that's going to be our principal curvatures. And what that means then is we can go one step further, which is, well, wait a second, that gives us eigenvectors then V1 and V2, right? But do you guys remember that symmetric matrices have their eigenvectors are orthogonal in your algebra? And you know, so it's a nice short simple proof of that, right? And so what that means then is if we use these as our basis vectors, then we get an A tilde, and guess what our A tilde is? It's just going to be lambda 1, lambda 2, and then 0 there and 0 there. So in other words, what we've learned here, and what's so nice and clean now, right, is that with the shape operator, you get, if you choose any orthogonal basis, you get a symmetric representation matrix A. But then that has two real eigenvalues and two eigenvectors, which, without, even if lambda 1 equals lambda 2, I have a duplicate V1 and V2, or all, I mean all the vectors are eigenvectors, but anyway, it doesn't matter. I can always choose two V1, V2 as my basis vectors so that my A tilde is actually diagonal, right? And then lambda 1 and lambda 2 are the principal curvature directions, and my basis vectors are orthogonal. Okay? And so we've proved that the principal curvature directions are always perpendicular, and we get these two real eigenvalues, which I'll prove next time are actually the curvatures along those cross sections of the surface. Yes?
So I guess like what sort of goes wrong if you're just looking at a plane,
Yep.
which doesn't have defined principal directions or curvatures? It seems like you can still define an orthonormal basis, and so maybe your matrix.
You need a symmetric operator.
Okay.
Right, so like we're using this identity here, right?
Yeah.
Only because of this identity is it that these two terms are equal. So to get for A to be symmetric, for us to prove, we had two things. First of all, we had to have an orthonormal basis so that we could use these formulas,
Yeah.
and we need this to equal that. In other words, we have to have a symmetric operator. So a symmetric operator with an orthonormal basis gives us a symmetric matrix representation with respect to that basis,
Yeah.
which can then be diagonalized. We all remember that if you have a symmetric matrix, then you can, it's basically just, you get typically two distinct eigenvalues, and then you can prove that the eigenvectors are perpendicular. That's a standard fact, by the way. It's just that if you just plug in right here this equation for V1 and V2, and then you'll get, what you end up getting is lambda 1 V1 dot V2 is equal to lambda 2 V1 dot V2. And so the point is that lambda 1 is not equal to lambda 2, that must be that V1 dot V2 is equal to 0. Okay. Now if lambda 1 and lambda 2 are equal, that means every vector is an eigenvalue, and your matrix is just a multiple of the identity. All right. Stick around after class if you have more questions, and I will see you guys on Wednesday. Good luck with the homework.